So we're going to look at induction, and the first thing I want to look at is just the logic behind an induction proof. Okay, so why we end up doing all the steps that we are. Just like any other proof, it's a series of statements, and those statements will be linked together using logical, what we call connectives. So Sn represents some statement, and that's the thing we're going to prove. S1 then is the first case. Sometimes you'll see it called the base case. Sk is when we generalize what it is we're trying to prove. So it's our assumption that we're going to make in our proof. And Sk plus 1 is the next case after the generalized one. That is the formal logic behind why induction works right there. And we'll see these symbols a lot more in extension 2. Some of these symbols you may not know what they are. That there represents and. So what it's saying is, in order to use induction, I need the base case and I need this other thing, and that there is implies. So if I've got Sk, that will imply Sk plus 1. That's an if-then statement, and that's basically your deductive proof. Deductive proofs are if-then statements, because you're saying, if I know this to be true, then this must be true. So you deduce it. So that inside the induction proof, there is a deduction to be done as well. If you've got both of those things, then that implies that our statement is true. Sn is true. So that's the logic behind it. So how do we structure it then? You don't have to write step 1 and step 2 in your proof. But I'm just saying, look, the first step I would do is I'll go and prove that base case, because we need to show that to be true. Usually it's n equals 1, but it might not always be n equals 1. Say they were proving it for even numbers, then your first case would be n equals 2. Once you've proven that, you're going to make an assumption, and essentially you just assume what it is that you're trying to prove. So we're going to assume that it is correct. When you're writing it out, you can write it in words like I just did there. Assume the result's true for n equals k, where k is some positive integer, or whatever condition it is that they've put on the problem. In set notation, you could write it that way. Assume it's true for n equals k, where k is an element of the positive integer, so it belongs in that set of numbers. Then we go and do our proof. So we're going to prove it's true for the next case, k plus 1. Well, if it was even numbers, it would be k plus 2. But whatever the next case is. When you finish your proof, you write a conclusion to it. But what's really important is that if-then statement. You say, I've shown that if-then condition, which means it's true. So we will end up showing that it is in fact true for k plus 1 if it's true for k. So if it's true for k, then it's true for k plus 1. That is so important in the conclusion. And that's why I've bolded the last bit. A lot of people leave off that bit, but that's the whole key to the proof. And then you conclude it. And you'll say, well, hang on, I can tie these two things together, because I know it's true for 1. But we just showed that if it's true for k, then it's true for k plus 1. So if it's true for 1, then it's true for 1 plus 1, 2. Now I know it's true for 2. If it's true for 2, then it's true for 2 plus 1, 3. Now I know it's true for 3. And you can keep going and keep going. And that's what's called inducing the solution. In set notation, I could write something like that. That upside down A means for all. So since it's true for n equals 1, then it's true for all n that are positive integers. And then you say, by induction, what technique have I used to go and do my proof? These first ones we're going to look at are a series. So all the series types. How do we approach this one? I mean, we have a formula for arithmetic series. We have a formula for geometric series. But they're not the only number patterns you could have. So here's a pattern, 1 squared plus 3 squared plus 5 squared. And the general term would be 2n minus 1 squared there. So a third n, 2n minus 1, 2n plus 1, that's what we're proposing the formula would be to find the sum to n. Let's prove it. First case, notice I didn't write step 1. Okay, first thing I'm going to do, prove it's true for n equals 1. Now the setting out of your proof. Reserve the right-hand side of your piece of paper for your explanations. We don't use columns. We've got a nice clean piece of paper. We have our proof, but then we have our explanation to the right. Now it will look like I'm using a column here, but that's because I'm comparing. So I'll say, well, look, the left-hand side of this, Well, the very first term is 1 squared. Sub that into 2n minus 1, you get 1. And that equals 1. The right-hand side, if I substitute it into the formula, I also get 1. So I'm making a comparison between these two things. And so yes, they are equal. The formula works for the first case. So hence, yes, I know that's true. That was one of the things I needed to prove, remember. I had to prove that base case. I've got it. I don't normally write that down, but that's just a highlight. Okay, we've got that S1. That was one of the things we had to get. So I'm now going to assume the result's true for n equals k, where k is a positive integer. Essentially, exactly what it is we're trying to prove, but instead of an n, I'm writing a k. It's always good to write out these things so you can see exactly what you got. So what am I going to prove? I want to prove it's true for k plus 1. So now, everywhere there's an n, I'm going to replace it with k plus 1. Write down what you're trying to prove. Because how do you know when you've got there if you don't write it down? So, and someone reading your proof needs to know what you're trying to do. So always write down, this is what I am trying to prove. Let's do the proof. Start with the left-hand side, that's series. Now the first step for these series type is pretty much the same. And I'm going to rewrite it, but with the second last term in there. The reason for doing that, again, I wouldn't normally put this here, it's just highlighting what we've got. That was the sum of the first k terms, our assumption if you like, plus this next term. That's what I want to get. Because now all of those plus ... I can replace with the assumption that we made. We assumed that all of that was 1/3 k, 2k minus 1, 2k plus 1, plus 2k plus 1 squared. And it's usually a good idea on the right to say something like that. Because how did I get, it's a proof. How did I get from the second line to the third line? It looks like magic. I've just replaced it. So I put an explanation down. I used my assumption. That's how I got there. Now, we've got to try and get to our answer that we're trying to prove. I'm not going to expand the whole thing out because if you look at what we're trying to prove, it has a common factor of 2k plus 1. So let's pull that out. No point expanding if I'm going to factorise it back in later. There is another common factor there, but it may not be obvious. And if you look at what we're trying to prove, it has a factor of 1/3. Both of these terms have a factor of 1/3. You may not see the 1/3, but if I pull it out, it now means I have 3 lots of 2k plus 1. So I pull out that 1/3 because I know what I'm trying to prove. It has a factor of 1/3. Pull it out. Now let's play what's left inside those brackets and hopefully we can show it as the other factors that we want. So expanding that out, grouping like terms, I've got a quadratic, 2k squared plus 5k plus 3, which factorises to be k plus 1, 2k plus 3, which if I'm not mistaken, that's what we were trying to prove. So now I say, yes, I've done it. Hence, my proof is true for k plus 1, but it's only true if my assumption was true. If my assumption's false, then my whole proof's a pack of garbage. So it's only true if it's also true for n equals k. That's why we must write that. What we're saying is, yes, I've proved it, but my proof only works if my assumption is correct. So what I've just done there is shown that if I've got sum of k, I can get sum of k plus 1. Now we tie it together. Well, hang on, we proved it was true for 1. So if it's true for 1, it's going to be true for 1 plus 1. You will see some people in their solutions actually write all this out. Since it's true for 1, then it's true for 1 plus 1, i.e. 2. And since it's true for 2, then it's true for 2 plus 1, i.e. 3. And so you don't need to do that. We can say, look, since we've done it for 1, then I now know it's going to be true for every integer by induction. I've induced the solution using my previous parts. So that's Sn proved. Let's do another one. This time you'll notice it's in sum notation. They didn't write the whole sum out. They've just given us the general term and we're going from k equals 1 to n. But it is still a series type. You might even like to write it out so you can get a feel for what's happening here. So the first term would be 1 on 1 times 3. The next one is 1 on 3 times 5. And now we can say, okay, in the denominator, we're multiplying consecutive odd numbers together. That's what we've got. We want to show this sum is n on 2n plus 1. Okay, let's see if it works for the first case. N equals 1. Left-hand side, the very first term is a third. Right-hand side, sub it into our formula. Yes, we get a third. Show the substitution step, because you're showing that this formula works. Don't just go, oh, right-hand side equals a third. You beaut, it works. Show the substitution step. So the left-hand side does equal the right-hand side, so we know it's true for n equals 1. We make our assumption. We assume what it is we're trying to prove. You could write it in some notation, or you could write out the series. Up to you. We're going to prove it's true for k plus 1. Again, I'm going to write out what it is that I'm trying to prove. Proof. So I write it out, but now I'll rewrite it, including the second last term, to highlight, hey, that's my assumption. I'm going to substitute in for my assumption, k on 2k plus 1. Now I've got to play around with the algebraic fractions and try and get this k plus 1 on 2k plus 3. So pull it together. We'll get a common denominator of 2k plus 1, 2k plus 3. Top of the fraction on the left-hand side, we get k, 2k plus 3. And I haven't done anything with the right-hand side because the denominator was already 2k plus 1, 2k plus 3. 2k squared plus 3k plus 1, which factorises to be 2k plus 1k plus 1. The 2k plus 1s cancel. That was what we were trying to prove. Hence it's true for k plus 1, if it's also true for k. And since we showed it was true for 1, got to be true for all of them by induction. Remember, there are 3 key parts to your induction proof. There's the setup. So we prove it true for the first case. We make our assumption, and then we state what we're trying to prove. So that's the setup. Then we go and do the proof. But this is actually a deductive proof we're now doing. So provide explanations, certainly for non-obvious steps. How did I go from this line to this line? Explain what you're doing. And you should conclude with your if-then statement. And then the final bit just ties the 2 parts together. I've proven it's true for 1, therefore it must be true for all of them by induction. Let's have a go at some of those.